In the name of God. Hello, dear students. My name is Masoud. I'm a physics teacher. We are in Ferho's website at your service to explain physics curriculum. So far, we talked about some topics in physics. We solved some problem actually within the textbook. I prepared some questions by myself. I solved and answered some problems and questions of national exam question. Right now, I'm gonna dive in with new subject, which is tangential, let's say, acceleration versus angular acceleration. So this subject concentrates on what? This subject concentrates on the relationship between two things, between tangential acceleration, which is AT, right? Tangential acceleration AT, and what? AT and angular acceleration omega. Does tangential acceleration have to do with, let's say, angular, excuse me, it's not omega, this one is alpha, right? Because angular acceleration is alpha. Does tangential acceleration AT have to do with alpha or not? Let me, let's say, explain this subject for you. I'm gonna start this subject with a very simple example, right? We have, for example, golf club, right? We have a golf club and we have a golf ball. Actually, the golfer should strike the ball with the golf club. Actually, in this situation, if the person swings the club around its body, it's more efficient than strike it normally, right? So whenever the person swings it, what does it mean? When this person swings the club, what happens to the, for example, motion? What happens to the motion of the club? Actually, the club moves in a circular track, and the head of the club, keep in mind that the entire club has what? Has a circular, has a rotational motion, let's say. Has a rotational motion, but the head of the club has a tangential, let's say, motion. This tangential motion is called tangential acceleration, AT, right? And so I told you, the golf club, let's say, is rotated. So it picks up what? The golf club picks up alpha because it rotates. Simultaneously, the head of the club picks up tangential acceleration because head of the club does not rotate. It just it just moves, let's say, toward the tangent of the circular track. That's why you see in this simple example, we let's say we connect two things together. We linked AT, tangential acceleration, and angular acceleration. That's why, and I want to add one more note. The larger the alpha is, the larger the tangential acceleration is. The more the rotation is, the greater the tangential acceleration is. And what does it mean? Simply, we can say they are alpha and tangential acceleration are, let's say, directly related to one another, right? And by this, let's say, by doing so, actually, the person can hit the ball with a great force in this situation. When the person swings the club, when the athlete provides a circular track for the club, actually the strike is more efficient than the normal, let's say, case. I mean normal case, I mean just strike it normally without swinging the club, I mean. Just move it in a straight line and strike the ball. Actually, it's not more efficient, right? And that's it. We have and we have one more example. Actually, let me read the let's say explained it in advance for you. I right now I'm gonna read the definition for tangential acceleration, and we have one more example. Tangential acceleration, or AT. From now, we denote tangential acceleration as AT, A sub t, right? AT means tangential acceleration. Is tangential acceleration, before I read the definition, before you read the screen actually, I have a question for you. Is tangential acceleration linear acceleration or rotational quantity? Think about it. So, because I say tangential, or tangent means, let's say, it's a straight line drawn along the circular track, right? It's a straight line. That's why it can't be angular acceleration. It belongs to the linear quantity. So tangential acceleration is the time rate of what? Time rate of change of the tangential speed. You see? So we define tangential acceleration by means of tangential speed. What does it mean? It means AT is equal to delta VT divided by delta T. Mathematically, I can write AT is equal to delta VT divided by delta T. Let's say read it. So this definition, let's say, takes out from this rule actually, is a time rate means divided by time. The phenomenon has taken place during a time interval. That's why we say the time rate of what? The time rate of change. Delta means change. The time rate of change of tangential velocity is called tangential acceleration. So we have a car here. The car rounds the circle. It moves along a circular track, and it picks up tangential acceleration, like the tangential velocity. They have the same, actually, they have the same direction. Whenever, let's say, for example, you are asked to mention or determine VT here for this car. Let's say, what shall you do? You have to say, teacher, this arrow is for AT and VT as well, right? So because they are parallel to one another, VT and AT are parallel to one another, that's why this arrow becomes VT and AT simultaneously, right? So, but actually they are different in let's say, concept. Actually, they are different in meaning. They are different, but as a direction, and when you are asked to determine the arrow for VT and AT, you have to use only one arrow because they are parallel to one another. They overlap with one another. They overlap each other. So let's move on to a table. We have a table which compares two things together: tangential acceleration AT and angular acceleration alpha. Right? Tangential acceleration and angular acceleration. Actually, angular, the right side of the table is background for us. It's not new for us. We know this information. We got this information already actually right now. But this one, the left side of the table, is new information. Tangential acceleration, AT, yeah? Tangential acceleration, AT. The first thing, actually the first point, it mentions the definition. It says the instantaneous linear acceleration, right? It's a new definition. Instantaneous linear acceleration for an object directed along a tangent to the object's circular path. So keep in mind that tangential acceleration is a instantaneous acceleration. What do I mean by instantaneous? Means at each instant, actually, there's a certain value for acceleration. It's not an average. I told you average means one number. And average, let's say, if you say average of some quantity, does not involve very accurate information because it focuses only on one value. Whereas in a, for example, circular track, when the particle, let's say, circles the nucleus of an atom, when a car circles the square, at each, let's say, moment, at each instant, at each position, this object has its own tangential acceleration, has its own tangential velocity. That's why instantaneous quantities are more accurate than average quantities. This is the difference between instantaneous and average quantities. So, instantaneous linear acceleration of an object directed along the tangent to the object's circular path. What do you say about angular acceleration? It's a background for us. It's not new. The time rate of change of angular speed means alpha is equal to, let me write it for alpha is equal to delta omega divided by delta t. But what do you say about this one? At is equal to delta vt divided by delta t. The second difference, tangential acceleration, or AT, is found by this relationship, this equation. AT is equal to r alpha, but angular acceleration, just rearrange the question for what? Rearrange the equation, excuse me. Rearrange the equation for alpha. Alpha is equal to AT over r. AT over r. Number 3, tangential acceleration, or AT, expressed in meter per second square. It's expressed in meter per second square, AT, because it's a linear quantity. Angular acceleration expressed in rad per second square because it's rotational quantity. Number 4, tangential acceleration, or AT, depends on the object's distance from the axis of rotation. What does it mean? Like the previous case, like the tangential speed, the farther the object is from the axis of rotation, the greater the tangential acceleration. The farther the object from the axis of rotation, the greater the tangential acceleration, right? What does it mean? It means R is directly proportional to AT. Farther points, farther horses on a merry-go-round actually have greater tangential acceleration than near, let's say, than nearer points, right? Nearer horses. For angular acceleration, the fourth case is angular acceleration is independent of the object's distance from the axis of rotation. What does it mean? Regardless of the distance, right? Irrespective of the distance, all points of the points of the, let's say, of the objects along the circular path have the same angular acceleration, right? All horses on the carousel or merry-go-round have the same omega. Otherwise, the object loses its rigidity. Yeah, otherwise the object deforms. And I told you this is a dangerous situation, right? Let's move on to other. Let's say we have some notes here. I wrote some notes for you about the table, actually. When R is required, right? When R is required in a question, you can rearrange this equation. You can rearrange it for finding R. R is equal to, if R is unknown, right? Anything that multiplies by the unknown, it goes to the denominator, and the other part goes to the numerator. So R is equal to AT over alpha, right? This is the first note. The second one, proof of the equation AT is equal to R alpha. I've told you over and over again, actually, the proof is important. The proof matters, actually. For understanding the subject, it matters, actually. Some student ask me, teacher, where does this rule come from, actually? What's the source of this rule? What's the origin of this rule? We can, let's say, let's say I proved it for you. I just read the steps for you, and I explain the steps, let's say, one by one. The first one, So we want to prove AT is equal to R alpha. We have to start from VT is equal to R omega, right? Focus on the equation of VT, tangential velocity by means of radius and omega, right? So right now, VT, let's say I told you in the beginning of our subject, and I've told you actually in previous lessons that acceleration is nothing but changing speed. Change in speed means acceleration, right? So delta V means acceleration. That's why when tangential velocity changes, actually, and this change is taking place during a time interval. That's why you have to add delta here in front of the delta V. In front of the VT, you have to write delta because velocity, let's say changing means acceleration. And this change, I told you, occurred in a time interval, in a particular time. That's why you have to divide it by delta t is equal to R omega. R does not change actually. The radius of the, for example, merry-go-round does not change. It's constant. But the only thing that changes in the right side, it's omega. So omega becomes delta omega, divided by delta t. So delta, the left part of the equation. The left part of the equation, delta Vt divided by delta t means delta V means time rate. Time rate of change of tangential speed means AT. Tangential acceleration is equal to R remains as it is. Just let's say brings it down. Just bring it down actually. I want you to write it as it is. Delta omega divided by delta t means time rate of change of angular speed means alpha. And the equation is this. AT is equal to R alpha if delta t approaches zero, if time interval is very short. What happens actually to the equation? We have a note here. The alpha represents instantaneous, you see? If the time interval is very short, right? Let's say alpha represents angular acceleration, not instantaneous. It represents instantaneous acceleration, not average angular acceleration, right? That's it. Thank you very much, guys, for watching this video, and bye-bye.